Welcome to this first podcast of Math-S400, Mathematics and Economic Modeling. This course deals a lot with mathematics, so we're going to see a lot of proofs, we're going to see several theorems, and we're also going to go over the proofs of these theorems, and we'll try to understand the proofs, and we'll try to understand the logic and the validity of these proofs. So in order to understand the proof, it's very important that you understand how a proof is made, how it's built up, what kind of logical steps are possible, and which kind of steps are not possible. So this is the reason why in the first part of this lecture I'm going to give you a quick introduction on logic, the logical connectives, the truth value of a proposal, and also the different kinds of proofs that we can use in order to demonstrate a theorem or a result in mathematics. So without further ado, let's go to the whiteboard. Okay, so here's my piece of paper and I have a pen. So I'm going to take notes with my pen so you can follow along while going. So in mathematics there are two kinds of values that are important, right? So something can either be true, right, or false. In mathematics it's very easy, either something is true or something is false, but it cannot be something in between or else. Okay, so for true we can write T, and for F we can write F, or even easier, for true we can give it the number 1, and then for false we give it the number 0, right? So if you in this lecture, if you see somewhere a 0, it means that it is false. If you see somewhere a 1, then it means that this is true. Okay, so what is true or what is false? Well, we're going to assert the trueness or the falseness of certain things, and these things are called formulas or propositions. Okay, so what is a formula? You can think of a formula as something that has been, it's like a Lego construction, in the sense that if you have two constructions in Lego, you can add them together to form a new one, right? So you can combine formulas into new formulas. In some cases you can also decompose a formula into separate pieces. So basically formulas are built up from other formulas and can be decomposed in other formulas, but similar to Lego construction, you have to start from something. And in mathematics, this thing that we start from, this is called an atomic statement. Okay, so what's an atomic statement? Basically, it's a building block of a formula. So we can write it, we will use notation P, small p, or Q, sometimes R or S. Okay, and these can stand for something that's either true or it's false. And it can be anything. So for example, P can be, it rains. It's just a simple sentence that's either true or false. Okay, so Q can be something like, mathematics is fun, which is obviously true, right? But sometimes it can also be false, right? So it's a simple statement that can be either true or false, and we don't attach particular meaning to what's, for the moment we don't really attach a lot of weight to what it means, right? What the sentence is. It's just something that is either true or false. Okay, so now that we have something to start with, let's look at how we can, what are the rules in order to make a formula into a new formula, and how to combine formulas into new ones. Okay, so first way how you can transform a formula into a new formula is by negation. Negation. So what do? We start with a formula, let's say P, and then we can negate the formula, and we write this negation of P is written down like this, right? So we have a horizontal bar and a vertical bar, and we put them in this kind of angle, and this is the negation of P. And if we have P, then we pronounce this as not P. Okay, so what's the idea? The idea is that if P is true, then not P is false, right? So we flip the truth value, and if P is false, then not P is true. Okay, so we can put this in what we call a truth table. So what's a truth table? Well, it's a simple table, and in the first row of the table you put a formula, and then below the formula you put the possible values that this formula can take. So here you have formula P, and P can be either false, which we denote by 0, or it can be true, which we denote by 1. And then next to it we can put the values of not P. So if P is false, then not P will be equal to 1. If P is equal to 1, then not P is equal to 0. So this is how we can get the value of not P from the value of P. So what can we do? We can also take, for example, the negation of P. Okay, we only have seen one way in order to transform a formula into a new one. So we can always take the negation of a formula. So this is a formula, we take the negation of this formula. So what's the value of not P? Well, you just have to invert the value of not P. So the first line gives you 0 and the second line gives you 1. And surprise, surprise, you see that, for example, this first column is equal to this third column. So we have our first logical result, which states that P, and let me write 3 lines here to show equivalence in terms of formulas. So the truth value of P will always be equal than the truth value of negative P. Okay. So you can negate the formula and then you can negate it again, and what do you get in the end? Well, in the end you get back the original formula. And of course, if you can double negate the formula, you can also triple negate the formula. And if you do this, you have to negate this formula here. You get 0, 1, and you get just negation of P, right? So every even number of negations you can cancel out. Okay, so this is the first way how to take a formula and turn it into a new formula. Now let's look at a second, perhaps a little bit more interesting way, in the sense that it combines 2 formulas into a new one. And the second way how to combine formulas into a new one, this is called conjunction. So for conjunction, what do we have? We start with 2 formulas, let's say P and Q, and then from these 2 formulas we make a new formula, and we combine this as a symbol. We write this upside down V, and we pronounce this as formula as P and Q. Okay, so you write down like this, but you pronounce it as P and Q. So what's the idea about conjunction? The idea is that if this formula P and Q is true, only if both P is true and Q is true, right? So if we write down the table, we have P and Q. What are the possible values of P and Q? Well, either both are false. P is false and Q is true. P is true and Q is false, or they are both true. And then if you look at the formula P and Q, so if both P and Q are false, then P and Q is also false, right? They're not both equal to true. If P is false and Q is true, then P and Q is false. If P is true, Q is false, P and Q is false. And if they are both true, then P and Q is true. Okay, so the only way where P and Q is true, when this formula is true, only when both P is true and Q is true. Okay. So we have seen negation and conjunction. So what can we do? For example, we can take the negation of P and Q. How do we derive this formula? Well, we simply take the formula P and Q and we negate the formula. So if we have a 0 here, we will have a 1 here. This will become a 1, this will become a 1, and this will become 0. Instead of negating P and Q, we can also negate P, negate the formula Q, and then take the conjunction between the two. So here, negating P would give you 1, negating Q would give you 1, 1, and 1. This would be true. Negating P would be 1 here, and then 0 here. 1 and 0, this would be 0. 0 and 1, this would be 0. And if you negate both 1s, you get 2 zeros, and this will be 0. Okay, we see that not P and not Q only has 1 at row 1, but not P and Q has 3 1s and then 0. So these two formulas are not the same. So this is maybe an interesting remark, is that if you negate P and Q, then this is not the same formula as first negating P, then negating Q, and then taking the AND operator. So it's very important where the brackets are. You cannot simply put the negation into the brackets. In some way you can put the negation into the brackets, and you will see this in a minute, but then you have to change something else. You cannot just negate both clauses and take the AND and expect this to be the same thing as the negation of the AND clause. So we had negation conjunction. So let me turn my piece of paper so we can continue. The third way to make new formulas is by disjunction. Okay, so we have a formula P, we have a formula Q, and the disjunction of P and Q is written with this V. Now it's not an upside down V, it's simply a V. And we pronounce this as P or Q. So what's the idea? The idea is that this formula P or Q is true if P is true or Q is true, right? So one of the two has to be true. And this is an inclusive OR. What this inclusive means, it means that P is true or Q is true, or they can also be both true. Okay, so this is opposite an exclusive OR. In an exclusive OR, either P is true or Q is true, but they are not both true. With an inclusive OR, it might be the case that both are true. Right, this is also valid. So if we pronounce OR in mathematics, we always mean an inclusive OR. So if we write down the table, PQ and then P or Q, we have the value 0, 0, 0, 1, 1, 0, and 1, 1. If both P and Q are 0, then P or Q is 0. If P is 0 and Q is 1, then P or Q is 1. If P is 1 and Q is 0, then P or Q is 1. And if both P and Q are 1, then it's inclusive OR, so P or Q is also equal to 1. Good. We can negate this formula. Let's see what happens then. Well, we only have to negate this column here. So we obtain 1, 0, 0, 0. So if I look at the previous table, here not P and not Q was 1, 0, 0, 0. If we negate P or Q, I also get 1, 0, 0, 0. So independent of the value of P and Q, we always get the same truth value of these two formulas, which means that they are the same. They're the same formula. So not P or Q is the same formula as not P and not Q. And similar, you can derive this also in a truth table. So please go ahead if you're not sure. If you negate P and Q, then this is the same as not P or not Q. If it's not the case that P or Q is true, then either P is false or Q is false. If it's not the case that both P and Q are true, then either P is false or Q is false. Okay, so that's the reasoning behind this. So if you know something about set theory, probably you know the rule that's called De Morgan's law. So if you have two sets A and B, and if you take the complement of the intersection, you get the complement of A union complement of B. And if you take the complement of the union, you can also write this as the complement of A intersection complement of B. So these two laws are very similar to these two laws in logic. Intersection here is similar to the AND operator, union is similar to the OR operator, and taking complements is similar to negating the formula. So there's some kind of there's a lot of similarity between set theory and propositional logic, and this is one of them. So if you know De Morgan's laws, you will probably also remember these important identities. Good. So negation, conjunction, disjunction. Let's go to the fourth way to combine formulas into new ones, and this is called implication. So for implication, we start with the formula P, we start with the formula Q, and then we make a new formula, and you have a P and then an arrow from left to right. This is an arrow to Q. And we, in words, we say that P implies Q. And often in theorems and in texts, you also see the phrasing, if P, then Q. So there's a lot of theorems in mathematics that start something like, if blah 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 is satisfied, then also this is satisfied. Basically, this is an if then, so this entails an implication. This is this formula that they want to express. So what's the idea behind the implication? The idea is that this formula is true. When is this formula true? Well, the condition for this to be true is that whenever P is true, then Q also has to be true, right? So this is basically the backbone behind this formula. So maybe it's easier if I write that in the true table. So if you have P, Q, P implies Q. So what are the possible values of P and Q? You have two zeros, 0, 1, 1, 0, and 1, 1. So P if Q, if P is false and Q is false, then P implies Q is true. Okay, so the idea is that whenever P is false, it doesn't matter what follows, right? The implication is always true. So here also in the second line, P is false, so we don't really care what happens with Q. So also here, this is true. The third one, you have to pay close attention. So here P is true, but Q is false, right? So in this case, it's not the case that validity of P also implies validity of Q. So this is the third line will be false. And in the last line, P is true, but also Q is true. So indeed, the validity of P implies the validity of Q. So here we have 1. Okay. So this is an important application. Is something many students have problems with, but it's just a logical consequence. So either whenever P is false, this is always true, no matter what. If P is true, then P implies Q is only valid whenever Q is true. So we have an important equivalent of implication. Basically, P implies Q. So let's look at the formula not P or Q. If you look at not P or Q, so we have a 1 and a 0. So we negate P but not Q. 1, 0. Here we have 1. Here we have 1, 1. Here we have 1. Here we have 0 and a 0. So we have 0, right, with an OR. And here we have a 0 and a 1. So we have 1. So these two columns are the same. So we have an equivalence in the formula that P implies Q is the same as stating not P or Q. And we can write this third formula in a different way. So we can try to take the negation outside. So what do we need to do? Well, we look back at De Morgan's laws. If you take the negation outside, we have to change the OR into an AND. And we have to negate each of these two formulas. So negating negative P gives you negative negative P. So this is P, and negating Q gives you negative Q. Right? So it's not the case that P is true and Q is false. So when will this be true? Well, we have the same formula here. Okay. So this is also equivalent to negative P and not Q. So P implies Q whenever it's not the case that P is true and Q is false. I was outside of the scope of my camera. So to recall, P implies Q is the same as saying that it's not the case that P is true and Q is false. So these three equivalences are quite important to remember because we will use them over and over again in the duration of this course. Good. So this is the fourth way how to make new formulas, and then there's a final way. So this is 5, and this is called equivalence, or I will call it equivalence. I think in the literature it's sometimes called bivalence or something, but I will call it equivalence. So we have a formula P, we have a formula Q, and then we have instead of an arrow from P to Q, now we have a double-sided arrow from P to Q and from Q to P. And to pronounce this, to pronounce this formula, we say P if and only if Q. If you don't like to write down this if and only if in full, often you write if, but then with two F's. P if Q. So simply P if and only if Q. So when is this formula true? Well, this formula will be true whenever the value of P is equal to the value of Q. Okay, either both true or both false. So if you have P, Q, P if and only if Q, you have all the possible values of P and Q. So if both are false, then you have a 1. If P is false and Q is true, then the values are not the same, so we have a 0. If P is true and Q is false, they're not the same, so we have a 0. And if both P and Q are true, then we have a 1. So remember, we had P implies Q. We have 1, 1, 0, 1. If you look at Q implies P, so here we have 1, here we have 0. 1 implies 0 is false. Right, so we have 0. Here Q is 0, so we have a 1, and here we have a 1. So if we take P implies Q and Q implies P, so we take the AND of this formula and this formula, so 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, and 1 and 1 is 1. And you see that this column here is exactly the same as this column here. So we get the equivalence P if and only if Q is the same as P implies Q and Q implies P. So in order to show that P if and only if Q, you can show that P implies Q, you can show that Q implies P, and because you have shown that both are true, then the AND will be true, so we have an equivalence. Okay, so this is how many times it goes when you want to prove a theorem that says something blah 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 if and only if something else, then you show that the first thing implies the second thing and the second thing implies the first thing, and then you have shown the equivalence between the two. So let me also put this into a box. Okay, so with these rules you should be able to get the truth value of many formulas. So you can make very complicated formulas by just stacking and combining different formulas into one. So for example, let me write down on the top of my head P and Q implies negative Q. Okay, let's try this one. P and Q implies negative Q. So we have P, Q, if you want to draw the truth table, 0, 0, 0, 1, 1, 0, on 1. So first we need P and Q. So 0, 0, 0, 1. Okay, we can derive negative Q. This is 1, 0, 1, 0. And then P and Q implies negative Q. What's the truth value of this? Does 0 imply 1? Well, no. Does 0 sorry. Of course, yes, because P and Q is false. Here also, because P and Q is false. Here P and Q is false, so this is a 1. And here we have a 1 and a 0, so this will be false. Alright, so we have the... So when will this be true? Well, whenever they're both false, P is false and Q is true, P is true or Q is false, and they'll be wrong when both are true. Okay, so how can you also see this? Well, one way to rewrite the first formula is first try to simplify the implication, right? So we have seen, for example, that P implies Q. This is the same as negative P or Q. Right, so if you use this here, substitute the implication, then you have negative P and Q or negative Q. Okay, and then we can use the Morgan's law for logic in order to simplify this first part here. So this becomes negative P or negative Q, and then or negative Q. And then this last one is 2 times the same thing, not Q or not Q, so this is simply not Q. So we have the formula negative P or negative Q. Okay, so this formula will be true whenever P is false or Q is false, right? So this is either here, 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 but not here because here both are true. Okay, so you can practice this at home. You write down a whole lot of formulas, you can write down the truth table, and then try to also do it by simplifying down the implications and using the different rules that we have seen in the course in order to make it easier to see whenever this formula is true or false. Okay, so these are the ways propositional logic with connectives. We're going to introduce 2 additional symbols to mainly to make our life easier, and these symbols are called quantifiers. So there are 2 quantifiers. The first quantifier is called the universal quantifier. Okay, so the universal quantifier, how do we write it down? It's written down as an upside down A, and it's used in the following way. You have an upside down A, and then you have an element, can be X, Y, Z, I don't care. So here I call it little a, and some said big A, and then a formula, and this formula can depend on this, called as a variable, this variable A. So how do we read this? We say that for all A in A, and then the formula PA. Okay, so for example, for all X in R, and then you have a formula, for example, X is lower or equal to 5. Okay, this can be a formula. Of course, this is false, but this is a valid formula with a quantifier. What is the idea of the upside down A, or the universal quantifier? So the universal quantifier is intuitively it's like a whole bunch of conjunctions. So for example, if A is a finite set, so that assumes that A is a set consisting of A1, A2 until AN. So this formula then is similar to saying PA1 and PA2 until PAN. Okay, so this formula will be true if and only if it is true for A1, it is true for A2, it is true for A3, and so on until AN. So the universal quantifier, or this formula here, is like a long chain of conjunctions ANDs. The advantage of using the universal quantifier is that it also is valid for sets that are infinite. Okay, so for example, A can be the set R. You cannot enumerate all the elements of R, but you can still write this formula down. Okay, so it's also valid for infinite sets. Okay, so this is the universal quantifier. There's a second one, and the second one is not the universal quantifier, but it's called the existential quantifier. And it's not an upside down E, because an upside down capital letter E is simply an E, but it's a reverse E. And then you have the same thing, A and A, and then the formula P that may depend on A. And how to pronounce it? We say there exists an A and A such that PA. Okay, for example, there exists an X and R such that X squared is equal to 1. Okay, so this is the formula P, and this is this first part here. So similar to above, if A is a finite set, for example A1 until AN, then this formula is the same as saying P A1 or P A2 or P A3 and so on until or P AN. So the universal quantifier is like a long chain of ANDs. The existential one is like a long chain of ORs. So in order for this to be true, it only has to be true for one of the elements in A. And now the advantage again is that it can also be used for infinite sets, right? So it is not only valid for finite sets. So let's look at the universal quantifier. We have for all A and A the formula PA, and let's see how we can negate this formula. Right, so you put the negation sign in front. So what happens now? If you negate this formula, this is the same as writing another formula, right? And how does this formula look like? Well, first you change the universal quantifier to an existential one. You copy the A and A, and then you have to remember to also negate the formula. So what's the underlying reason for this whole procedure? Well, remember that this is simply a long chain of ANDs, PA1 and PA2 and so on. So if you would negate this, then we can use Morgan's law. So what happens? All the ANDs become an OR, and you have to negate every part in the chain of ANDs. So this becomes negative PA1 or negative P2 and so on, or negative PAN. And this is exactly this formula here, right? So it's basically a shortcut of the Morgan's law for logic. Similarly, if you have an existential for all A, there exists an A and A such that PA, and then if you negate this, so first change the existential one to universal one, and then negate the premises, so you have negative PA. Okay. Good. And you can generalize this to chains of quantifiers. So for example, if you have for all A and A, there exists to be in B such that a formula which now depends on A and B. So let's assume that you would like to negate this. Then you change the for all into an existential one. You change the existential into a universal one. And then you have to negate the premises. Okay, so if it's not the case that for all A there exists a B such that PAB, then there should be an A such that for all B, PAB is false. Okay, so this is how you negate formulas with quantifiers. So let me give an example. Say for all X in R, there exists a Y in R such that X times Y is equal to 1. Okay, so this is obviously true. So if you want to negate this, what do we have? We have that there exists an X in R. So this is for all Y in R, X times Y is different from 1. Okay. So this is example 1. Let me think of another example. For all X in R and for all Y in R, X is bigger than 0 and Y is smaller than 0, then X times Y is smaller than 0. Okay, so let's try to negate this entire formula here. What do we need to do? First we have to change the uniform this quantifier to an existential one. Also this becomes an existential quantifier, and then you have to negate this entire formula. Okay, so if you look good, how does this formula look like? Well, first we have a part here, and we have an implication, and then we have another formula here. So this looks similar to P implies Q. So we have to negate a P implies Q. Okay, so if you remember, if you have a P implies Q, what's the negation of this? Well, P implies Q was the same as negative P or Q. And then using De Morgan's law, you have that this is the same as changing the or into an and negating both parts. So this becomes P and negative Q. Okay, so this is something to remember. Negating an implication is the same. If it's not the case that P implies Q, then P is true and Q is false. Okay, so what we need to do, we have to copy P. So we have X bigger than 0 and Y is smaller than 0, and take an and negating Q. So and X times Y is greater or equal to 0. Okay, so this is the negation of this. Okay, so this is important. Write down a lot of formulas, try to negate them. So normally changing the quantifiers is quite easy, but then you also have to negate the premises, right? So exercise a lot in doing this, how to negate implications, negate equivalences, and so on and so on. Okay, so there are some remarks in terms of quantifiers that I would like to spell out. So the first remark has to do with rearranging the order of the quantifiers. Okay, so for example, if you have two quantifiers for all A and for all B and B, PAB, and you would like to know if you can exchange this first part here with the second part here. So you can write for all B and B and for all A and A, PAB. Okay, so the difference between this formula and this formula is that here the B is up front and the A is second, and here the A is up front and the B is second. Okay. So was this remember that a for all is like a long chain of ants, right? So it's a long chain of ants where first you iterate over the b's, right? And then once you have done this, you iterate over the a's. And here you first iterate over all the a's and then you iterate over the b's. So this is basically a long chain of ants. This is a long chain of ants, but the order in which the a's and the b's appear is the same, is different. And you can show that these two formulas are the same, right? So if you have two universal quantifiers, there's no loss in generality of first putting b and then a, or first putting a and then b. And the same holds if you have two existentials quantifiers. So there exists an a and there exists a b such that PAB is the same as saying there exists a b and there exists an a such that PAB. Okay. Now there's a bit of problem when the quantifiers are different. So for example, for all a and a, there exists a b and b, PAB, and on the right side you have there exists an a. Let me delete this. The right hand side you have there exists a b such that for all a and a, PAB. Okay, so here you have first the for all and then the existential one. Here you have first the existential one and then the universal one. So are these two formulas the same? So let's think a little bit. So here you have that for all a, small a, there exists a b such that this formula is true. So in this case the b may depend on the a, right? So for different a's, for different elements in set a, you can take a different b, right? So the only thing that's required here is that for every a there exists a b. On the right hand side you start with the b, and then for this particular b the PAB has to hold for every a. Okay, so here this b may depend on a, right? So for different a's you can take different b's. In this case you have to take the b first, so this b may not depend on a, right? You have to take the b, and then for this particular b it has to hold for every a. Okay, so it turns out that this is much stronger, right? Because you cannot take the b depending on the a. So we have that this formula implies this formula, but not the other way around. Okay. So you have to be careful when mixing up quantifiers with each other. You can exchange two universal quantifiers and you can exchange two existential quantifiers. You cannot exchange a universal and an existential quantifier and expect them to give you the same formula, because this one is much stronger than this one. Okay, so far we have seen formulas, we have seen quantifiers, so I think it's time to take a short break, a mental pause with some footage of a baby bunny. So in the second part of this lecture, we're going to go over the different types of proof techniques or different types of proofs that you have in mathematics. So a first type of proof that's used very often is called a direct proof. Okay, so for example, assume that you want to prove that P implies Q, right? So P is a formula, Q is a formula, and you want to show that P implies Q. So what's a direct proof? Well, a direct proof first, for example, shows that P implies some formula. Let's call it P0. Okay, so that's the first step. And then in the second step, you show that P0 implies some formula. Let's call it P1. And then in the next step, you show that P1 implies P2, and then you show that this implies P3, and so on. So in the end, you get a formula, let's say Pn, and then finally you show that Pn implies Q. right? So you have a long chain of implications, one following from the other. So what do you know? You know that if P is true, then P0 has to be true, right? Because this implication is true. And then if P0 is true, then P1 has to be true. And then if P1 is true, then P2 has to be true, and so on, until in the end, you know that if P is true, then Pn is true, and if Pn is true, then Q is true. So what you have shown, having these long chains of deductions, that P implies Q. Okay, so let me give an example. This is an example of the book. So the thing we're going to prove is the following. If for all integers x, if x is odd, then x squared is odd. Okay, so this is the theorem, simple theorem, but this is a theorem that we're going to prove. And here you see you have the application, right? If then, this means that you have a formula P that says that x is odd, and you have a formula Q that says that x squared is odd, and you have to show that P implies Q. Okay, so that's the thing they want us to prove. So let's start with P. X is odd. So we would like to find the first consequence of this fact. So we can use the definition of being an odd number. So when is a number odd? The number is odd if it's 2 times another number plus 1. Okay, so any number is even if it's 2 times another number. It is odd if it's 2 times another number plus 1. Okay, so a consequence of this is that there exists a number k. So let me write it like this. There exists a number k in the numbers such that x is equal to 2 times k plus 1. Okay. So you want to get a chain and somehow end up with q. And q says something about x squared. Okay, so here it's a bit of a guesswork. What's going to be p1, what's going to be p2, and so on, right? So this is not entirely clear, but we want to go into the direction of x squared. Okay, so what would be a good thing? Well, a good thing would be to take the square of this x. Okay, so if x is 2k plus 1, then x squared is equal to 2k plus 1 squared. Okay, so from this we can work out this square here. So we have that x squared is equal to 4k squared plus 4k plus 1 squared, which is 1. And you see that we can write this as x squared is equal to, we can take this term and this term together. So this is 2 times 2k squared plus 2k and then plus 1. And we're almost there, right? So we have that x squared is equal to 2 times z plus 1, where z is 2k squared plus 2k, right? So this is just a number in n. So we finally arrive at the fact that x squared is odd, right? Why is it odd? Because it's 2 times the number z plus 1. Okay, so this is the definition of an odd number. Alright, so this is how the proof works. You start with the left hand side of the application P, you get some deductions, and then finally you end up with Q. Okay. This is a direct proof. It's used very often in mathematics. So let's go to a second kind of proof. This is the proof by contrapositive. So what's a contrapositive? I don't think I have said it yet, but let's go to the truth table of P implies Q. So we have 0, 0, 0, 1, 1, 0, 1, 1. P implies Q. you have 1, 1, 0, 1. So now let's look at negative q implies negative p. Okay, so let's invert this. You have 1 implies 1, this is okay. You have 0 implies 1, this is also okay. You have 1 implies 0, this is not okay. And then we have 0 implies 0, this is also okay. So what do we see? We see that this column here is the same as this column here. Okay, so you have an important equivalence. Again, an important equivalence of implication is that P implies Q is the same as negative Q implies negative P. Okay, and this negative Q implies negative P is called the contrapositive of P implies Q. So this is also an important equivalence to remember. Okay, so what's the idea of a proof by contrapositive? We can show that P implies Q. How can we do this? Well, basically we have to show that negative Q implies negative P. So we show that P implies Q by a direct proof that negative Q implies negative P. Right, so we start with negative Q, we get a number of intermediate formulas, and finally we hope to end up with negative P. Okay, so let's try to give an example. So the following is what we're going to prove. We're going to prove that if the sum of two integers is even, x plus y is even, then either both x and y are even, or both x and y are odd. Okay, so if you have two numbers x and y, if the sum is even, then there either are both even or there are both odd, but it's impossible that one is even and the other one is odd. Okay, good, let's try to prove this. So what do we do? So we first have to find the P and the Q. So here we have an important then, right? If then, so this is the implication. So what everything that's before the then, this is going to be my P, and then this is going to be my Q. Okay, so P is the sum of two integers x and y is even, and then Q is that both x and y are even or both x and y are odd. Okay, so there's also important things here. There's an and here and an and here, and then there's an or, right? So this is basically an x is even and y is even, or x is odd and y is odd. Okay, so Q is the same as x is even and y is even, or x is odd and y is odd. Okay, so first step in the proof by contrapositive is to find negative Q. So the first step here is to negate this Q. So what's the negation of this? Okay, so we're going to put this whole thing between brackets and we're going to negate this, right? So this is an or, so the or turns into an and. Okay, so here we have an and, here we have an or, here we have an and. Okay, and then you have to negate this part and you have to negate this part inside the and. This is de Morgan's law. So let's see what happens. We have negation of x is even and y is even, and negation of x is odd and y is odd. Okay, Now we have a negation of something with an AND. Here we have a negation of something with an AND. So we know how to put a negation inside. We negate this part to this part and we change the AND into an OR. And the same here. Okay, so if we negate X is even, we have X is odd or Y is odd. Okay, and sorry, X is even or Y is even. Okay, so negative Q, right, this is negative Q, is the same as X is odd or Y is odd and X is even or Y is even. Okay, so we can look at the different combinations, right? So either one of these two is true or one of these two is true and one of these has to be true and one of these has to be true, right? So in the first case, X is odd and X is even. Okay, this is clearly impossible. X is either odd or even, so this will always be false. Okay. Second case, X is odd and Y is even. All right, so that's an option. And Y is even. Third option, Y is odd and X is even. X is even. And then the fourth option, Y is odd and Y is even. This is clearly impossible because I is either odd or even, but cannot be both, right? So basically what two cases we have is that X is odd and Y is even, or Y is odd and X is even. Okay, so intuitively, in practice, you don't need to make this entire deduction by negating. I just wanted to do here in terms of the exercise, but you can clearly see that if it's not the case that both X or Y are even, or they're both odd, then one of the two has to be odd and the other one has to be even, or vice versa. All right, so this is basically what's stated here. Either X is odd and Y is even, or Y is odd and X is even. Okay, so this is negative Q, right? So negative Q, X is even and Y is odd, or vice versa. Okay, so let's assume that X is even and Y is odd, and then we can say, okay, the other case holds by analogy. Okay, so first deduction that follows from this is that X is equal to 2 times K for some K, and Y is equal to 2 times Z plus 1 for some K and N, and for some Z and N. Okay, so there are numbers K and Z such that X is 2 times K, X is even, 2 times the number, and Y is odd, so it's 2 times the number plus 1. We would like to end up with negative P, the sum of two integers X plus Y is even, so we would like to show that the sum of the two integers X plus Y is odd, right? So we want to show X plus Y is odd. This is negative P. Okay, so how do we get to negative P? Well, we just take the sum of X and Y. So we have that X plus Y is equal to 2 times K plus 2 times Z plus 1. This is equal to 2 times K plus Z plus 1. It's 2 times R plus 1, where R is equal to K plus Z. So we see that X plus Y is odd, and this is the same as negative P. Okay, so we have shown that negative Q implies negative P. And if you take the case where Y is even and X is odd, you will get entirely the same deduction, right? So you just have to switch X and Y around here, and you also get negative P. Okay, so in both cases we have shown that negative Q implies negative P. Okay, good. So we have direct proof. You have a proof by contrapositive, which is in a certain sense a direct proof in disguise, because it uses the same kind of reasoning as a direct proof, and the only difference is that you start with negative Q and you try to show negative P. The third way of making a proof is the infamous proof by contradiction. Okay. So what's the proof by contradiction? Well, the main idea is the following. Let's say that you have a formula P and you want to show that P is true. Right? So to show P is true, well, what you can do is you can show that negative P is false. Okay, so what happens if you show that negative P is false? Well, then you know that negative P is true, and you know that negative P is equal to P. Okay, so in order to show that P is true, you can show that negative P is false. If you have shown that negative P is false, then negative P has to be true, and negative P is P, so you have shown that P is true. Okay, so that's the very basic intuition behind the proof by contradiction. Okay, and now the catch is the following. How do you show that negative P is false? Well, you show this by assuming that negative P is true and then get a contradiction. Okay, so what's a contradiction? And a contradiction in a certain way is the following, right? So you get a contradiction when you show something, let's call this formula R, and you also show that negative R, right? A contradiction is when you show that both R is true and negative R is true. Right? Once you have shown that the formula is true and also its negation is true, then you have a contradiction. So why is this the case? Well, if you have R and negative R, you have 0, 1, 1, 0. R and negative R, you have 0 and 0. So this is always false, right? So this is basically a contradiction. You cannot show that both R and negative R are true, right? In no cases this formula is true. Okay. So let's try to give you an example of a proof by contradiction. This is a famous example that you may already know or not know. It's with the following proposition. It says that square root of 2 is an irrational number. Okay, very easy proposition. So the formula is P. P says that square root of 2 is an irrational number. So we're going to prove this by contradiction. So what are we going to do? We're going to assume that negative P. What's negative P? Well, you have to negate P. Negative P says that square root of 2 is a rational number. So we're going to assume that this is true, right? Square root of 2 is a rational number, and then in some sense we're going to get a contradiction. Once we have the contradiction, we know that this is false, so this has to be true. Okay, so let's assume that negative P is true. From this it follows that square root of 2 is a rational number. So what's a rational number? A rational number is a number that can be written as a quotient of two whole numbers, right? So know that there exist numbers a and b and z such that square root of 2 is equal to a over b. Okay. So without loss of generality, not both a and b are even, right? So why is this without loss of generality? Well, if both a and b are even, you can divide both a and b by 2, right? And then you have 2 times the number, divide by 2 times the number, and you can get rid of the 2. And you can keep on doing this, right? Each time you get an even, 2 even numbers, you can divide both numerator and denominator by 2. How long can you do this? Well, you can do this until one of the two numbers is odd. Okay, so without loss of generality, either A or B is odd, right? They're not both even. Okay. So we have square root of 2 is A over B, so we can take B to the other side. We have B times square root of 2 is A. Okay. We have a square root of 2. Let's try to get rid of the square root. So we square both sides. Okay, if we square this side, we get B squared times 2 is equal to A squared. Okay. So we see that A squared is 2 times the number. So from this it follows that A squared is even. Okay. If A squared is even, then you can show that A is even. Okay, so this requires some argument in the sense that you have to show that if x squared is even, then x is even, right? So try this for yourself, try to prove this theorem, or try to prove this proposition. So this is an if-then, right? So it's P then Q. Okay, so you can either use the direct proof, you can try proof by contrapositive, but you should be able to show that if x squared is even, then x is even. Okay, so I leave it up to you to try this, but basically you can show that this is correct. A squared is even, then A is even. Okay, so what happens if A is even? Well, if A is even, then you know that there exists a K and Z such that A is 2 times K. So let's, if A is 2 times K, then A squared is equal to 4K squared. Okay, and we're going to substitute this back into this A squared here. Okay, so we get A squared is 4K squared is equal to 2 times B squared. So we can get rid of the 2 here and the 2 here. So you have 2K squared is equal to B squared. Then you have that B squared is even because it's 2 times the number. And then you can use this same result again to show that B is even. And now you have to be smart enough to stop. And then you say, stop, I have found the contradiction. Okay, so what's the contradiction? First we found that B is even. Along the way we also had that A is even, but somewhere upstairs here we assumed without loss of generality that not both of them are even. Okay, so if you take this here, then you get the contradiction. You have found an assumption and the contradiction of the same assumption. Right, so you have a contradiction, so you know that this is false, so this has to be true. Okay, this is a proof by contradiction. Good. There's one last proof that I want to give to you, a proof technique. I think we're at the 4th one. So we had the direct proof, we had the proof by contrapositive, we had the proof by contradiction, and now the last one is the proof by induction. So when do you use the proof by induction? You use the proof by induction if the thing you want to prove starts in the following way. You have that for all n natural numbers n, and then a formula that may depend on this n. Right? So proof by induction is only used to prove formulas of this form. So if I ask you to prove something and it starts with for all n and n, and then a formula, a light bulb should go up in your head saying, oh, maybe I can use a proof by induction. It's not always the case, but at least it's a possibility that you should strongly consider. Okay. So how does a proof by induction work? You probably already heard from this. So normally you have a base case, then you have the induction hypothesis. Okay, and with the base case and the induction hypothesis, you prove the induction. Okay, so what's the base case? The base case is showing that P of 1 is true. Okay. So what's then the induction? In the induction, you basically assume that P of n is true, and then you use this to show that Pn plus 1 is true. So in some sense, it shows that for all n in n, if P of n is true, then Pn plus 1 is true. Okay, so this is the induction step of the proof. And you show A and you show B. Once you have shown both, you say, oh, proof by induction, I have shown that this is true for all n. So how does this work? Well, intuitively, it's actually very easy. So you have shown P1, and then you also have shown this, and this holds for every n. Right, so in particular, it holds that if I plug in 1 here, then you have shown that P1 implies P2. Okay, so we know that P1 implies P2. If I plug in P2 here, then I have shown that P2 implies P3. So you have the implication from P2 to P3. If I plug in 3 here, you show that P3 implies P4, and so on until Pk, and then further on and so on. Right? So for every n I can think of, I can go back this entire chain. I know the first one is true, so the second one is true, so the third one is true, so the fourth one is true, and so on. So basically I have shown it for all n natural numbers. Okay, so this is the proof by induction. So let's give you an example. And the example asks you to prove that for all natural numbers n, the following holds. If I take the sum from I equal to 1 up to n of I get a number n times n plus 1 over 2. Good. So A, we're going to show that P1 is true. So here 1 is in place of n. Okay, so if I plug in 1 into the formula here, this is my Pn. Instead of n, if I plug in 1, I have to show that if I sum I from 1 to 1 of I get 1 times 2 over 2, which is equal to 1. Okay, so here I sum I from 1 to 1, so this gives me 1. On the right hand side I have 1. So P1 is very easy. You just plug in the numbers on the left and the right hand side and you show that they are equal. Now I have to show that Pn implies Pn plus 1. So this is my part A, this is my part B. Okay, so what's Pn? Pn is the fact that if I sum I equal from 1 to n of I get n times n plus 1 over 2. What's Pn plus 1? So instead of n, I now have n plus 1. So this is the sum from I1 to n plus 1, right? Instead of n, I now have n plus 1 of I. Instead of n, I have n plus 1. Here again, instead of n, I have n plus 1, but I have to add 1, so this becomes n plus 2, and then divided by 2. So I have to show that this implies this. Okay, so how do we show that this is true? Well, we start from the left hand side, and then along the way we hopefully get to the right hand side. So we start with sum I1 to n plus 1 of I. So we know that this holds, right? So we assume that this holds. We have to show that this holds. So what can we do? We can split up the sum up to n and then take the last term. So this is equal to sum up to n of I plus the last term, which is going to be equal to n plus 1. This sum, the first term here, we know that this is equal to n times n plus 1 over 2. So this is equal to n times n plus 1 over 2. And then we're left with n plus 1. Put everything on the common denominator. So we have n times n plus 1 plus 2 times n plus 1. Now take the n plus 1 terms together. You have n plus 1. How many of them do we have? We have n here, 2 here. So we have n plus 2 in total, divided by 2. And then we see that this here is equal to this here. So we have broken Pn plus 1 from Pn. So this is the proof by induction. Okay, so this is the final part of this introductory class into logic and proofs.